maintain radio communications for 5 days without power, a photovoltaic, also known as solar, system is recommended for remote site monitoring water tanks. The equipment requires 24 volts, 0.5 amps, which equals 12 watts. The radio uses 2 watts, so the total power consumption is 14 watts. Key system components include solar panels, a charge controller, and batteries. For solar panels, a 100-watt solar panel can provide approximately 600 watt-hours per day during peak sunlight hours. It is recommended to use 2 100-watt panels to ensure power production even in overcast conditions. A 24-volt, 20-amp charge controller is necessary to regulate charging and prevent overcharging. As for batteries, 2 12-volt, 200-amp-hour batteries connected in series for 24-volt operation are required. This setup provides 4,800 watt-hours of storage, sufficient to provide power for 5 days, assuming an average of 4 hours of sunlight per day. Here are 2 package recommendations. Firstly, the Renogy 500-watt solar kit, which includes 4 125-watt solar panels, a Renogy 30-amp charge controller, and 4 12-volt, 150-amp-hour batteries. Secondly, the Grape Solar 550-watt solar kit, which includes 2 360-watt solar panels, a Grape Solar 40-amp charge controller, and 2 12-volt, 105-amp-hour batteries. Additional considerations include mounting, cabling, maintenance, and a battery monitor. Fix the solar panels on a tilt mount to maximize sunlight exposure. Use heavy-duty cables to minimize losses. Clean the solar panels regularly to maintain efficiency. Consider using a battery monitor to track battery charge status. Finally, consult a qualified electrician for proper installation to ensure safety and performance. This system will provide reliable power to maintain radio communications for up to 5 days without grid power. The excess power generated during peak hours can be used to charge other devices or equipment. The calculation for this involves a few steps. Firstly, calculate the daily energy consumption. The total power consumption is 14 watts. Therefore, the daily energy consumption is 14 watts multiplied by 24 hours, which equals 336 watt-hours. Secondly, calculate the total energy required for 5 days. This is 336 watt-hours per day multiplied by 5 days, equaling 1680 watt-hours. Thirdly, consider the depth of discharge for the batteries. It is generally recommended to not fully discharge lead-acid batteries, so aim for a maximum depth of discharge of 50%. Fourthly, calculate the required battery capacity. To provide 1680 watt-hours with a 50% depth of discharge, you need a battery capacity of 1680 watt-hours divided by 0.5, which equals 3,360 watt-hours. Since you are using a 24-volt system, the required amp-hour capacity is 3,360 watt-hours divided by 24 volts, which equals 140 amp-hours. The recommended battery setup of 2 12-volt, 200 amp-hour batteries in series provides a total of 24 volts and 200 amp-hours, which is more than sufficient. The solar panels need to generate enough energy to replenish the battery each day. Assuming an average of 4 hours of sunlight per day, the solar panels need to generate at least 336 watt-hours per day. 2 100-watt panels provide 200 watts. So, the energy generated is 200 watts multiplied by 4 hours, which equals 800 watt-hours. This is more than enough to cover the daily energy consumption. Charge controller should be rated to handle the maximum current from the solar panels. The maximum current from the solar panels is approximately 200 watts divided by 24 volts, which equals 8.33 amps. A 20-amp charge controller is sufficient. When selecting components, it's important to consider the environmental conditions at the remote site. Solar panels should be rated for outdoor use and be able to withstand the local weather conditions such as wind, rain, and snow. Batteries should also be suitable for the temperature range at the site. Lithium batteries may be a better option than lead-acid batteries in extreme temperatures. The charge controller should be installed in a weatherproof enclosure to protect it from the elements. Proper wiring and grounding are essential for safety and performance. Use appropriately sized wires for the current and voltage of the system. Brand the solar panels, charge controller, and batteries according to local electrical codes. Regular maintenance is important to ensure the long-term performance of the system. Clean the solar panels regularly to remove any dirt or debris that may reduce their efficiency. Check the battery connections to ensure they are clean and tight. Monitor the battery voltage and state of charge to identify any potential problems. Replace the batteries every few years as needed. Consider using a remote monitoring system to track the performance of the solar power system. This can help you identify any problems early on and take corrective action. A remote monitoring system can also provide valuable data on energy production and consumption. The system can be expanded in the future if needed. For example, you could add more solar panels to increase energy production, or add more batteries to increase energy storage capacity. You could also add a backup generator to provide power in case of extended periods of low sunlight. The cost of a solar power system for remote water tank monitoring will vary depending on the size of the system and the quality of the components. However, the long-term benefits of solar power, such as reduced operating costs and increased reliability, can outweigh the initial investment. The total cost of ownership should be considered when evaluating different solar power system options. In addition to the cost of the components, there may be installation costs. It is always recommended to consult with a qualified electrician to ensure that the system is installed properly and safely. Obtaining multiple quotes from different installers can help you find the best price. Permits may be required for the installation of a solar power system. Check with the local building department to determine the permit requirements in area. Be sure to comply with all applicable electrical codes and regulations. Safety is paramount when working with electricity. Always disconnect the power before working on any electrical components. Wear appropriate personal protective equipment, such as gloves and eye protection. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Troubleshooting a solar power system can be complex. If you are experiencing problems with system, start by checking the basics. Make sure that the solar panels are clean and free of debris. Check the battery connections to ensure they are clean and tight. Verify that the charge controller is working properly. If you are still having problems, consult with a qualified electrician. Many resources are available to help with the design, installation, and maintenance of solar power systems. The Solar Energy Industries Association offers information on solar power technology, policy, and industry trends. The Interstate Renewable Energy Council provides training and certification for solar power professionals. Your local utility company may also offer rebates or incentives for solar power systems. Taking the time to research and plan a solar power system can ensure a reliable and cost-effective solution for remote water tank monitoring. Proper installation and maintenance are essential for long-term performance. By following these guidelines, one can confidently maintain radio communications for days without grid power. Selecting the right components ensures compatibility and optimal performance. Matching the solar panel voltage to the battery voltage is crucial for efficient charging. The charge controller acts as a bridge, regulating the flow of electricity. This prevents overcharging, which can damage the batteries. Battery capacity should be carefully calculated to meet energy demands. Considering potential future expansion of the system is beneficial. It is important to choose components that can accommodate future growth. A modular design allows for easy expansion without replacing the entire system. This scalable approach can save money in the long run. Integrating the solar power system with existing monitoring infrastructure ensures seamless operation. Compatibility with the radio communication equipment is vital. Verifying that the solar power system is compatible with the existing monitoring equipment prevents potential conflicts. A well-integrated system streamlines data collection and transmission. Regular data analysis helps optimize the performance of the system. Monitoring energy production and consumption patterns allows for fine-tuning the system for maximum efficiency. This data-driven approach can identify potential issues early on. By analyzing historical data, it's possible to predict future energy needs. A proactive approach ensures that the system can adapt to changing conditions. Properly maintaining the system guarantees long-term reliability. Regular inspections can identify wear and tear. Prompt repairs prevent minor issues from escalating into major problems. A proactive maintenance schedule minimizes downtime. Conducting periodic performance tests verifies that the system operates at peak efficiency. This testing ensures that all components function as intended. A comprehensive testing protocol includes voltage measurements, current readings, and battery capacity checks. The results can be compared against baseline data to identify any deviations. This approach can help detect early signs of degradation or malfunction. Protecting the system from environmental factors ensures long-term durability. Selecting weather-resistant components is crucial, especially in harsh climates. Implementing protective measures, such as enclosures, shields, and surge protectors, extends the lifespan of the system. This protection minimizes the risk of damage from weather events. Proper grounding and lightning protection safeguard the system from electrical surges. Grounding provides a path for stray currents to flow safely to the earth. Lightning protection diverts lightning strikes away from the system. These safety measures prevent damage to the equipment and reduce the risk of fire. Maximizing sunlight exposure optimizes energy production. Positioning the solar panels in an unobstructed location is essential. Adjusting the tilt, angle, and orientation of the panels to track the sun's movement maximizes energy capture. A solar tracking system can automatically adjust the panels throughout the day. This active tracking significantly increases energy production compared to fixed panels. Utilizing energy-efficient components minimizes energy consumption. Selecting radios and other monitoring equipment with low power consumption extends battery life. Optimizing the communication protocol reduces data transmission energy requirements. This efficiency lowers the overall energy demand, allowing for a smaller solar power system. Remote monitoring capabilities enable proactive management. A remote monitoring system allows for real-time data collection and analysis. Alerts and notifications can be configured to notify when issues arise. Remote control features enable the system to be adjusted from anywhere. This remote management capability enhances responsiveness and reduces the need for on-site visits. A comprehensive preventative maintenance plan prolongs the lifespan of the system, and this approach involves regular inspections and proactive repairs. A preventative maintenance plan is a long-term investment.